want to extend continuity. So now I have four equations with four unknown, x, y, z, velocity, and the pressure. The only thing left what's BC stand for? Boundary conditions. First, give me a domain, a geometry. You're solving a problem in the combustor can, and then you set up a mesh or grid, and then you apply this equation of continuity and Navier-Stokes. You get all that solved. At the edge of the domain, at the boundary, you have to impose the condition appropriate to your problem. And some of that will be examined in the next, which is your homework problem that you kind of play. Last but not least, you say, oh, well, okay, so this equation been existing for half a century. We must solve all the engineering problems by now, right? Because how hard can it be? Now we have computer and all that. There's no more need to hire any fluid mechanic engineer at a place like Pratt & Whitney. Wrong. It turns out we didn't have much time to dive into detail. When you have turbulence flow, which is 99% engineering problem, the equation has to be outputted to account for those small, unsteady, fluctuating flow. And the turbulence become the black box. Yeah, those equations, while they look elegant and look very tempting, without an appropriate turbulent model, you cannot have an accurate solution to the problem. And that's why people still need to hire fluid mechanic engineer. And the turbulent model is different for different problem. The flow behind an automobile, the turbulent model behind that weight is different between that and the turbulent model behind that of the turbine blade, etc., etc. So, with that, we can now look at this homework problem. I have 10 minutes to set you up, or actually do it for you, and you just have to repeat. All this detail. I have a problem of a sheet of liquid, so it's not air, so it's a little bit different. And obviously, if it's a liquid like water, think about water from a raindrop on the roof. And this sheet of water has a height h. Gravity is vertical. And let's read the problem statement very carefully because each word has important implication. Steady, laminar, meaning that I can use the Navier-Stokes equation as is, as presented by us now, because if it's turbulent, then the velocity has to be changed from u to u mean plus a fluctuating velocity due to turbulence. That's a much more in-depth discussion that is more for advanced fluid mechanics. So all the problem we have been dealing with is laminar flow. So I don't have to deal with turbulent modeling. It's viscous flow, obviously. This diagram represents a very wide plate. What does that mean to you? Translation. Wide inclined plate, meaning it's very big into and over the board. So what? What can you assume? What does that mean to you in layman terms? Anyone else? No?
Depth doesn't matter per unit.
Depth doesn't matter. You mean this depth? or this depth into the paper. Meaning, what does that mean? What does that mean? Unity per unit depth, but more importantly, it's a 2D problem. Two-dimensional problem. Which is stated in the problem too. So the sheet of water or liquid coming down the plate is driven partly by gravity, and it says so. So you cannot neglect gravity, because then you don't have a problem. H is a constant thickness. And here's a very important word that I hope you interpreted appropriately. Fully developed flow. Anyone remember when you've seen that before? Fully developed flow. Pipe flow, very good, pipe flow. Where we say fully developed, meaning the velocity profile, whatever shape it is. Fully developed, it doesn't change. It's already reached a plateau that the flow velocity profile, or specifically any variable to be determined with respect to distance x is 0. It's not changing with the streamwise direction, and hence the word fully developed. And that's very important for how we can simplify our Navier-Stokes equation. Do you understand this implication? Fully developed. Okay? The last one is also critical. You say free surface, meaning the water surface here. This is called a free surface. The water surface that's exposed to ambient with no shear stress. Remember what shear stress is defined as? We just went through that in the derivation of Navier-Stokes equation. Anyone? du dy. What that said is, at the free surface at height h, there's no shear. This term is 0. Now, with that as a problem statement, I have just 4 minutes to set you up with as much as I can to get you to do the homework. So, what it asks is to simplify the equation of continuity x momentum and y momentum, plus the appropriate boundary condition. The boundary are at 2 places, at the wall and the height h. And someone remind me what is the condition at the wall? Why at the wall, at y equal to 0? All the velocity has to be 0. What do we call that? The term is called no slip. Very good. At height h, free surface, no shear. Translation, that's the boundary condition. That's done for you. Continuity in 2D. This is density, not pressure. Can we simplify this? And be quick, because we're running out of time. What's the first term you could do? Change of something with time.
0.
Y. 0. Y. Steady. Very good. Second term. Change of something with respect to x. What does it mean to you as fully developed?
0.
Has to be 0. Reason? Fully developed. So what I left with is the fact that velocity v in the y direction with respect to y is 0, here's something you can think about. Applying the boundary condition, can you tell me what is v equal to? That's critical because that will further allow you to simplify the remaining xy momentum equation. Which I will do is give you the direction for the y equation, sorry, for the x equation, and let you, as your homework, work on the y equation without any hint. So here's the y equation. Sorry, I keep using the wrong word. This is the x equation. And the remaining 2 minutes, I want to show you what you can do to simplify it. And you're going to do the same thing for the other equation in the y direction as an assignment. And that's all. You don't have to do anything beyond that. Just to see what can be tossed out and why. Are you ready? Yes. What is dp, dx, and y? It's 0 because of what? It's a fully developed flow. Anything in the x direction is 0. G sub x, I think you can do, is a component of the gravity in the direction parallel to the plate. So it's either g sine theta or g cosine theta, you decide. Fully developed flow also implies the second derivative is also 0. So the term within this bracket is also 0. That's the left side. Only one term left, plus gravity. On the right side, steady state, 0. Fully developed,